Today we'll discuss more exponential growth and decay formulas and another interest formula called continually compounded interest. The growth and decay has a more general formula than we've seen before. It is A of t, which is basically the ending amount is equal to the initial amount multiplied by e raised to the kt. K is just a constant, it's some number, t is the time. Now if we have a k value that's greater than 0, it's going to be a growth, and a k value that's less than 0, it's going to be a decay. When we talk about continually compounding interest, that means interest that's compounded every second of every day, but it only levels out to a certain point because of this e exponential. Now, in this case, we have the final amount a is equal to the initial amount p given this interest rate over a period of time. So we'll use all these in today's examples. First one starts out as a growth and decay problem because it doesn't say anything about continually compounding. We know that in 1970 we got 222 million, and in 2007 we've got 300 million. And if the growth is exponential, they tell us that right off the bat, and that needs to be told to us. We got to write an equation that models the growth. We don't have to do any solving in this case. So what we do is we start out with the initial amount, which we've got 222 million. I'm just going to use the 222. That's equal to e to the kt. But in this case, we go from 1970 to 2007. So that ends up being a total of 37 years. And we end up with 300 million. And if I could put the millions, but the zeros are going to all cancel out, so we'll be fine. And then solving this we'll get to in a minute, but that's a setup. Here's another situation where you have a bacteria colony starting with 100 million bacteria at one time, grows exponentially, and you want to know what's going on there. Here's a situation where you've got a bacteria colony starting off with 100 million at 2 p.m. and grows exponentially. At 5 million, we know we've got 110 million bacteria, so that's e to the k, and it's gone 3 hours. We want to know how many bacteria there are at 10:30 p.m. Well, the problem is that's another time. So what we've got to do is we have to first find our k value in order to find the time. So let's go ahead and do that. We first of all divide 110 by 100, that's 1.1, is equal to e to the 3k. Now using natural logarithms, we can take the natural log of both sides, and we know when we have the natural log, just do it, natural log of e to the 3k. We get to bring that 3k out in front. So I have the natural log of 1.1 is equal to 3k ln e. We know that ln e is 1, so I just divide by 3, and ln 1.1 over 3 is equal to k. Now I'm going to leave this like this rather than do a decimal approximation and put it into our second equation. In the second equation, we wanted to know how many bacteria there are if I start with 100 at 2 p.m. and go till 10 p.m. So that's 8.5 hours, and I have a k value now. So I have a k value of ln 1.1 over 3 times from 2 o'clock to 10:30 is 8.5. And now we're looking for this new number x. So what I'm going to do is I'm just going to grind this out in my calculator. And after plugging it into our calculator, we get roughly 131 million. So in this next problem, it talks about the half-life of carbon being 5,800 years. Half-life is the time it takes for half of a material to decompose. And we want to determine how much carbon is left after 4,000 years if the initial amount is 38 grams. So let's type in what we know. We know we start with 38 grams. We have some E raised to the K. They didn't give us a K in this case, so again we've got to find that. T power. Well, we got a couple of numbers here. We know that the half-life is 5,800 years, and then we've got 4,000 again. So this looks a lot like our last problem. So what we've got to do is we have to first use the fact that this half-life is 5,800 years. Now, if it takes 5,800 years for half of this stuff to decompose, then I need to take half of 38 to determine how much is left. So I have 19 left. And that would happen over a course of 5,800 years. Again, we're going to need to solve for K. When I divide 38 to the other side, I get 0.5 is equal to E to the 5,800 K. Take the natural log of both sides, just like in the last example. I get 5,800 K ln E, but we know ln E is 1. So now I have the natural log of 0.5 over 5,800 is equal to K. And once again, just like in the last problem, we want to know how much is left after 4,000 years, so we're looking for an unknown. We're starting with 38. We have E to this new K ln 0.5 over 5,800 times 4,000 years. And we're doing this problem just to introduce the concept of half-life. You can have a third life, fourth life, whatever. So let's plug that into the calculator, and I get roughly 23.56. So now we talk investments, and we want to make $7,000 on an investment of $20,000 and choose an account that compounds monthly. This is kind of important. At a rate of 7.25% yearly. How long will your money have to stay in the account? So even though we talked in the initial slide about continually compounding interest, this is not the case. This is our typical monthly compounding equation. So we remember that equation is A equals P times 1 minus, or plus in this case, R over N to the NT. So in this case, we want to make $7,000 from $20,000, so we end up with $27,000. Start with $20,000. 1 plus our rate is 0.725. Compounded monthly, that's 12 times a year, raised to the 12 times T is which we're going to solve for. So now we've got to do some division. I've got 27 over 20 equals 1 plus 0.0725 over 12 raised to the 12t. I need to be able to solve for this t, so now I have to use either natural logarithms or common logarithms. I'll just use a natural logarithm. So I'm going to say the natural log of 27 over 20 is equal to 12t times the natural log of 1 plus 0.0725 over 12. Now I got to get t isolated. So again, this is just going to be an ugly looking problem, but it's going to turn into a calculator problem, so no worries. So once again, I divide by the 12 and the natural log of 1 plus 0.0725 over 12. And once again, we said it's going to turn into a calculator problem, so we plug this in and we end up with a time of roughly 4.15 years. So now let's go to an investment where we talk continually compounding. We want to double our money and choose to invest in an account that compounds continuously, in this case, at a 7% annual rate. And how long must we keep the money in? So this is A of t equals P e to the RT. So we start out with an unknown amount of money. We can pick any amount we want. I'll just pick $100. And we want to double it, so we want to go to $200. And we take e to the rate, which is 0.07, times t. Again, I divide, get e to the 0.07 t. We need to solve for t, so we need to take the natural log of both sides. Natural log of 2 is equal to 0.07 t times the natural log of e. The natural log of e is 1 once again, so I just divide by 0.07. I get the natural log of 2 over 0.07 is equal to the time. So in this case, the time's going. So in this case, the time will be equal to approximately 9.9 years. And that's all we've got. Make sure you fill out your survey and do your Connect Ed. And we'll talk more tomorrow.